everyone, I am Harsh and today we are going to discuss the third problem from CP-31 sheet by TLE Eliminators under the 1100 rated problems. So let's move on to the CP-31 sheet. As you can see, I have the 1100 rating parameter box ticked and here is the clickable link to your problem. So let's move on to the third problem. So the name of the problem is collecting K. So let's go through the problem statement. You are given an array A of n positive integers and a score. If your score is greater than or equal to AI, then you can increase your score by AI and remove AI from the array. So for each index I, you need to output the maximum number of additional array elements that you can remove if you remove AI and then set your score to AI. Note that the removal of AI should not be counted in your answer. So looking up to the constraints, T is of the order of 5000, N is of the order of 10 power 5 and elements in the array are of the order of 10 power 9. And it is guaranteed that sum of n over all the test cases does not exceed 10 power 5. Great. So what actually is mentioned in the question? Let's understand the question via the help of one of the test cases. So let's take up this test case and understand what the question actually wants us to do. So in the question they have given you an array. So first of all they have given you the size of the array 5 and then they have given you the array elements 25, 4, 1, 2. Now what you need to do is you have to choose each and every element of the array as the first element. For let's suppose I start choosing with this particular index, okay? And what you do is you set your score to the value of the array element that you have chosen. So you set your score to 4. Now, in the question they have said that you can take any element that have the value lesser than equal to your current score. So since my current score is 4, just tell me, if I started with 4, my current score is 4 and once I take an element, I have to remove that element from the array. So this element gets removed. Now tell me the next possible elements that I can take. I can take 1, I can take 2. Can I take 5 or 20? Can I? The answer is no, right? I can't take 5 and 20 because my current score is 4. So let's take this 1 and 2 and let's remove them from the array. Once I do so, once I am taking any element, the value of the element gets added to my score. So tell me my updated score, what my score became. My score became 4 plus 1 plus 2, that is nothing but 7. Agree? Now tell me the next element I can take. I can take this 5 as well, right? Because this 5 is lesser than equals to 7, so I can take 5 as well. So now my score becomes 7 plus 5, which is equal to 12. Now can I take 20? The answer is no. Okay. So the maximum number of elements I can take is 5, 4, 1, 2. Now, when I started with 5, when I started with 4, that is the element present at index 2. According to zero-based indexing. So when I started with an element present at index 2, tell me the maximum number of additional elements I was able to take. If you look, I was able to take this 1, 2 and 5. That is additionally I was able to take 3 more elements. Do you all agree? So for starting element as the value present at this particular index, we were able to obtain 3 more additional elements. So the answer for this particular index will be 3. Similarly, the question tells you that what will be the answer if we start with this element, then this element, then this element, then this element and this element. So you need to basically tell me the answer for each of the index of the array as the starting element. I hope the question is clear. So how we can solve this? So before moving on to the solution, first of all, the first thing that we should keep in our mind is what's the expected time complexity of our code. So if you look up, the n is of the order of 10 power 5, isn't it? So we can have any solution, something like that works in big O of n log n square root of n, big O of n, big O of n log n, big O of n square root n, or big O of log n, or something like square root n. Anything lesser than n square root n will work. But you can't have time complexity like n square square root of n. This is something that is not allowed. So you have to keep your time complexity within this range, within the range of n square root of n, isn't it? So let's proceed now how we can actually solve this. So let's understand the solution with the help of this particular example only. And let's suppose this is our starting element. If this is our starting element, can I say my score is 4? And can I say that this 4, I can't take this 4 anymore? Can I say this? The answer is yes. Now tell me, can I take this 5 right now? Can I? The answer is a clear no. I can't take this 5 right now. But what are the elements I can take right now? I can take this 1, I can take this 2, isn't it? So let's take them. If I take them, what's the benefit? Just keep in mind, whenever we are taking any element, the value of the element gets added to our score. And as our score increases, the increased score help us to take other elements as well. Like for example, right over here, we can't take 4 right now, but once we take 1 and 2 and our score gets updated to 7, I can take 5 now. So what's the lesson I have learned? What's the lesson? The lesson is that when I tell you that my score is 4, so let's greedily take all the elements that have the score lesser than equals to 4. Let's take them first. And once we take them, our score increases. And once our score increases, then check for other elements what I can take. This is going to be our approach to this question. Now, how we can actually do this? So to do that, when I say you that, let's suppose I have my initial score as 4 and let's take all the elements that are lesser than equals to 4. So don't you think that if we have the array sorted, if we have array something like this 1, 2, 4, 5, 20, we can do that task very easily. That let's suppose I tell you I have started with 4. So can I then, if my array is sorted, so I will be able to say that okay, take all the elements that are towards the left. Take all those elements. I can say that very easily. And how can we get the sum of all the elements towards the left? By maintaining a simple prefix sum. So that's the motivation that help us to think that okay, we can sort the array. But just at the back of the mind, keep one thing, that you have to return your answer according to the index. That is, the first number that you are going to print will be the answer corresponding to this value 20. The second number that you are going to print will be the answer corresponding to this value 5, and so on. So whenever you are sorting your array, you have to preserve the original index as well. So you will not only keep the values, you will actually maintain a vector of pair of int comma end, and along with the values, you will keep their indexes as well. So if I just do the same thing over here, so the indexes are 1, 3, 2, 4, 4, 2, 5, 1, and 20, 0. These are the indexes. Okay. So now we have started with 4. Once let's suppose our starting element is 4. If I say you my starting element is 4, so I can always take the elements that are towards the left of it. That is something that I can always do. So tell me the additional elements till now I have taken. Additional elements. Would you all agree that the number of additional elements that I have taken till now is 2? Because I can take all the elements towards the left, and if my current index is 2, that is I am currently standing at I equals to 2, so I can take all the elements towards the left, and since this is a zero based indexing, so this value will be equals to I only. You can see we have 2 elements towards the left. So the additional elements that we have taken is left. And can you all say me what my score right now? What my score right now? My score is nothing but the sum of values till this particular index. So my score is nothing but 7. Okay. Now what I will do? I will move step by step. I will just move on to this index and check that can I take this index? The answer is yes, I can take this index. So what I will do is I will increase my additional value by 1, so my additional value becomes 3, and I will increment my score becomes 12. Then I will check that can I take this element, the answer will be no, that I can't take, so I will stop over here. Now just imagine one thing. If I say you that you are standing over here, you took all the elements towards the left, and now you are moving one by one to check that whether you can take these elements or not. Wouldn't that give the time complexity of big O of n squared in worst case? Because for every index I, you are traversing all the elements towards the right. So wouldn't that give a time complexity of big O of n squared in worst case? So this is something that we can't do because we have the n of the order of 10 power 5. So this will something that will give TLE. So how we can just neglect this step? So let me tell you, if the elements were, let's suppose, I'm just writing down the elements for now, not writing the indexes. Okay. So let's suppose elements were something like this. So 1, 2, 4, 6, 7, 7, 8. Okay. And 9. Now tell me one thing. And let me take one more element. And let's suppose 40. Now tell me one thing. If I say you that you are currently standing over here, so you can take all the elements towards the left, right? And your score will become 7. Your score will become 7. Now with this 7 score, can't you take all these elements? Now there are two options. Either you make a jump of 1 and 1 and go to each and every element and check whether you can take these elements or not. Or you have an option that you make a bigger jump to over here. Because currently you have the score of 7. And with that particular score, you can take all these elements. So wouldn't it be favorable that if you make a bigger jump? So this is something that we will try to do. We will try to do a bigger jump. And once you do a bigger jump, can I say that my score, when I reach to this particular index, will be nothing but the sum of all these values? And I can easily maintain this value via prefix sum. So what I will do is, what my logic will be, that from here I will jump over here, I will update my score with the prefix sum of this particular index, and from here I will now again see that whether to which particular jump I can make. If I reach to any particular index from where I can't move forward, or this is the end value of the array, I will completely stop. And that will be the last element that I can take. This is going to be the logic behind this question. Now the only thing left is how we will make this jump. Like if we wouldn't have had these pairs as values, and if we would have had this direct 1D values, so what we would have done? If we have a current score of 7, we would have just applied lower bound of 8. Why lower bound of 8 and not 7? Tell me. This is because what I am going to do is, I want, if I, let's suppose I am currently over here 4 and I have multiple 7s, so I can take all these 7s, right? So I have to jump to this particular index. Right? So to do that, what I am doing is, I am doing the lower bound of 7 plus 1, that is 8. I will reach to this particular index, and I will just do, if this gives me idx, so I will just do simply idx minus minus and go to last 7. Because if we directly apply lower bound of 7, I will get this particular answer, right? So this is something that I am not going to do. I am going to do lower bound of 7 plus 1, that is 8, and I am going to reach, and I am going to do a simple idx minus minus and going to reach the last 7. But we don't have the direct values over here. We actually have the values as pairs. So how do we actually apply lower bound in pairs? So see, it's a very common method. You know that what actually matters, value matters. Do index matters? The answer is no. So what you are going to do over here, you are going to apply lower bound of your pair value will be, if your score is, let's suppose 4. So you are going to apply lower bound at 4 plus 1, comma, int mean. Why this int mean? Just think, why this int mean? This is because if this value satisfies what we actually want, if this value 7 is satisfying the lower bound of 7, if this actually satisfies what we want, so this second value should not interfere. Now if this second value is the lowest integer value, if this is the lowest integer value, so if the first value passes the case, so second value always be. Like for example, over here, if I just simply apply lower bound of 8 commas int mean. So first of all, what it will do? It will find in the array that where the first value is greater than equals to 8. So it will reach to this particular index. Now whatever is the index value of this particular pair element, will it matter? Will it force this lower bound value to go forward, or will it stop over here? It will stop over here, right? Because the first value satisfies the condition that the element is greater than equals to 8, and the second value will always satisfy that the value is greater than equals to int mean. So for finding the lower bound in pairs in vector that contain pair as elements, we do something like this, because we only want the lower bound value on the basis of first values, right? So for index, we kept the lowest possible value, so that if the first value passes the condition, the second will always be. So if I summarize the approach, what we are going to do, first of all, we are sort our array, and to maintain the original index, we are going to store the values in pairs, and then we are going to sort, and then we are going to each and every element. We are taking all the elements towards this left, and after that we are applying lower bound continuously in this array and checking to which further elements we can take. This is going to be the approach for this question. So let's see the code for better understanding. So this is actually the code to this question. Let me zoom in. So first of all, I took the number of test cases as input, then I took the value of n as input and constructed a pair of long, comma, long. And the reason is clear that why we are constructing the pair. So then we took n elements as inputs. First of all, I am taking the element as input, and in my vector I am pushing back a along with its original index. Okay. Then I constructed a prefix vector of size n for the very specific reason that we always, when we are at an index, our score will be nothing but the prefix sum till that particular score, till that prefix sum till that particular index. That will be our score, right? So for that reason, we are constructing the prefix sum, and we shorted this vector v. So let's populate this prefix sum vector. So the first value will be nothing but the first value in this vector, and for all the subsequent indexes, pre of I will be nothing but pre of I minus 1 plus v of I dot first. So because first value in the vector contains the value and the second value contains the original index. So this is how you constructed the prefix sum. Then we constructed a vector LL answer of size n, and we are going to each and every index, and we will consider that particular index as our start value. So first of all, we are going to I, each particular I. Whenever we go to I, tell me the additional elements that you have taken till now. Tell me. The number of additional elements that you have taken till now is nothing but I. Do you all agree? Because if you are at I, you have total I plus 1 elements, isn't it? And therefore the number of additional elements that you have taken, not considering the first one, the number of additional elements that you have taken is nothing but I plus 1 minus 1. That is nothing but I. And your current index is j, because you are initially standing at I. Now while your j is lesser than n, you are going to find the lower bound of pre of j plus 1 comma int mean in your vector, because pre of j is your current score. If you are standing at j, what is your score? Your score is pre of j. So you are going to find the lower bound of pre of j plus 1 comma int mean in your vector, and whatever index you get, you are going to subtract minus 1 from there, isn't it? Why we are subtracting minus 1? Because we have taken plus 1 value over here. So to go to the last suitable value, we are subtracting minus 1. Now if this index is j, what does this mean? This means that we were initially standing at j, and the index that we have got is still j. So we are not able to move even a single element forward. In that case, what we will do is we will simply break. We can't take any more elements. If this is not the case, so the number of additional elements that I will be able to take is nothing but idx minus j. So simply added that value to my found variable, and my index shifts to idx. Once this happens, so for this current element, what is my original index? My original index is v of I dot second, right? So in my original index in my answer vector, I simply store this value fine. And then once I have stored values for each and every index, I simply iterate over this answer vector and print the answer. This is actually the code to this question. What's the time complexity? If you look, this loop runs for n. This loop runs for n log n. This is a shorting, so shorting takes time of n log n. This loop runs for n, and this loop runs for n, isn't it? And inside this loop, you are applying binary search, so we can say that this loop runs for n log n, and again then this loop runs for n. So the total time complexity, you can say that is the maximum of all these values, that is nothing but big of n log n, isn't it? What's the space complexity? What's the space complexity? If you look, we have constructed a vector v that are going to store n elements. So over here we have a space of n. Then we have constructed a prefix vector which again is of size n, and an answer vector that is of size n, and some variables. So you can say that okay, you have a space complexity of big of n. So this is the time and space complexity, which is well under the range, and it will give you AC for your submission. So I hope all of you got it. Thank you.